Good morning, students. So, in the previous classroom discussion topic, we had a discussion on how these hardware components like register file and arithmetic logic unit are connected to the processor. So that we have seen, and how this register file will be implemented by making use of a single memory block, and another way is two memory blocks. That also we have seen that. So today, in classroom discussion topic, we are going to discuss about this data path. So now I would like to share my screen. So is my screen is visible to you? Yeah. So here the data path is the today's topic for discussion. So the lecture objectives is that this session will develop the students' knowledge on the data path of a processor. So generally, we already familiar with that about this instruction processing. So it consisting of two phases, that is the fetch phase and the execution phase. So that we have familiar already about these two different phases of the instruction execution, fetch and execution phase of this instruction execution. So it is a convenient way to divide the processor hardware into two corresponding sections, as similar to this one section fetches the instructions and another execute that instructions. So the section of the hardware which fetches the instructions is also responsible for decoding of that instruction and generating the control signals that causes the appropriate actions to take place in the execution of the instruction. So the execution section will read the data operands specified in an instruction and then performs the required computation and store the results. So this is a five-stage organization of the hardware we are using. So in the first stage, which is called it as the instruction fetch stage, and second stage is source registers, and then the third phase is the arithmetic logic unit, which is used for performing all the arithmetic and logic operations. And stage 4 is memory access, and then after completion of this arithmetic logic operation, so whatever the result we are going to get, that is going to be stored in the destination registers at stage 5. So this is a 5-stage organization of the hardware which is used for instruction execution as well as the fetch cycles. So the actions taken in each of the 5 stages are completed in one clock cycle. An instruction is fetched in step 1 by hardware stage 1 and placed into IR instruction register, and it is decoded, and its source registers are read in step 2, and the information in the IR is used to generate the control signals for all subsequent steps. Therefore, IR must continue to hold the instruction until its execution is completed. So it is necessary to insert registers between stages, which is called it as a interstage registers. So these interstage registers are used in every stage of execution of this instruction. So which is used for storing of the intermediate results, so that it will be carry forwarded that values from one stage to the another stage, so that they can act as an inputs to the next stage during the next clock cycle. So this is the diagram which we already familiar with, that how this register file is connected to the ALU that we have seen. Okay, so this part we have seen, this part we have seen that. Now we have adding an extra part here which is called it as the memory address and then memory data we are using here. So here the intermediate registers we are using, which is used for storing of these values of the operands. A, which is used, RA is the register which is used for storing of the A operand, and RB is the corresponding to B. And then if it is an immediate value or the register value, based on that the mux B, the multiplexer associated with that will select. If it is a register operand, the selection is 0. If it is an immediate operand, the selection is 1, and that will act as the input B for arithmetic logic unit. And this A will be directly coming from RA, which is as acting as an input A for this arithmetic logic unit. And whatever this output generated by this arithmetic logic unit, that is going to be stored in RZ register. Fine. So this is also here. If it is RB, so it is also selected here, and then this value is also be stored in RM register. So this is a memory operand if it is having that. Okay, so this is what we are going to get here. This is a stage 2 and stage 3 arithmetic logic operation will be carried out, and this is the stage 4, so which will fetch the memory operands values, and then it will going to store that address values here. So this is again we are using mux y we are using here, so which is used here for the selection of this memory address as well as memory data. So it corresponds to stage 2 to stage 5 of 5 stage instruction hardware. So here the data read from the register file are placed in registers RA and RB. Okay, so whatever the data we are reading from the register file A and B, which is placed in RA and RB registers, and register RA provides the data to input INA of the arithmetic logic unit, and multiplexer must be forwards either the contents of RB or the immediate value in the instruction register to ALU's second input, which is called it as IN input B. The ALU constitutes stage 3, and the result of the computation is performed and placed in a register RZ. Okay, after completion of that ALU operation. Fine. So recall that for computational instructions such as an add instruction, no processing actions takes place in step 4, and during that step, multiplexer mux y in the above data path selects the RZ register RZ to transfer the result of the computation to RY. So the contents of RY are transferred to the register file in step 5 and loaded into the destination register. Okay, so that is what it is done here. So that is the arithmetic logic instructions, how it will be executed. So if you consider the load and store instruction types, the data path for load and store instructions, so the effective address of the memory operand is computed by the ALU in step 3 and loaded into the register RZ. So from there it is sent to the memory which is in stage 4. So this is the difference you have to identify when we are using the load and store instruction and the 5 stage hardware is used here. So now if you see that load instruction here, so the data read from the memory are selected by multiplexer mux y and placed in register ry to be transferred to the register file in the next clock cycle. So for store instruction, data are read from the register file, so which is a part of stage 2 and placed in register rb. Okay, and since memory access is done in stage 4, so another interstage register is needed to maintain correct data flow in the multi-stage structure. So the data to be stored are moved from RB to RM in step 3 and from there to the memory in step 4. So that is what the difference we can observe between load instruction and store instruction. So no action is taken in step 5 in this case when we are going for the store instruction. So the subroutine call instructions, whenever you take subroutine call instructions, that is nothing but function calls if you take it as. So it will require to save the return address in a general purpose register that is generally called as a link register. We are using that. Fine. So now the point is that it is a time for reflection spot 1. So what is the purpose of RM register and as well as link registers? So the link register is used in whenever we are making use of the subroutine calls. and rm is used when we are using this store instruction data path, right? So this is the instruction fetch section, how the hardware is implemented in the processor for instruction fetch. So what is it is using here is that control circuit is there here, and then this is a register file via RA and RY. So instruction address generator will be there. So this instruction address generator will make use of this program counter register, and this program counter register is incremented. So that is nothing but whatever the address that is there in the register are that, or whether it has to take this program counter. So the mux MA is going to select either 0 or 1. Based on that, it has to generate the memory address. Similarly, the corresponding memory data has to be generated. So the mux B, so immediate value extended to 32-bit here, then the control circuit will make use of this instruction register, and it can able to perform this control circuit. It can perform this instruction decoding, and then based on that, it is able to generate the next instruction address. It is going to generate that. And then this is a circuit for instruction address generator, so which we can call it as here. And this instruction address generator is nothing but here mux multiplexer corresponding to this program counter is taken here, whether it has to consider the input from RA register, or the input which is acting it as an adder output will be given as an input to this mux. Okay, so this adder output is given as an input to the mux here. So it will select that whether the mux PC will select 0 or 1. If it is 0, RA register content will be selected. If it is 1, the outcome of this adder will be selected, and it will be placed into the PC. Fine. So this will be coming here. And if it is an immediate value, so this branch offset will be selected here. Otherwise, program counter is incremented with 4. That is a word length. So mux incrementer will be there. So whether we have to increment the PC value by 4, or whether we have to increment with the offset. So that is given to the adder circuit here. Okay, then that will be given stored in the PC temp register. So this is what we are calling it as a written address mux y. So this is how the instruction address generator will be used for generating that addresses. So that today's based on this today's lecture, we have a problem here. So write the contents of different interstage registers when we are executing the instruction add R2, R3, R4. So this is the lecture level practice problem for the today's session. So any doubts? So if you don't have any doubts, now I would like to stop my session.